associated with a bad outcome for neck, something we think we've demonstrated, and I must say that others have suggested this in prior work. The effect is most apparent for infants born at less than or equal to 27 weeks gestational age. I can't answer the question, is this the cause of necrotizing enterocolitis, or is it only a biomarker? If it's only a biomarker, we can work with that. We got to prevent neck. We got to do better than this. We cannot wait until a child has a bloody stool at 3 in the morning and the abdomen is distended to begin to address this problem. If we can identify this bacterial population, and those of you in the audience who are starting to think, I need a problem to bring my technology to, this is a fantastic one. We got to do better predicting it, and predicting it may be that we will be looking at the microbial populations. Now, lest I leave you with the conclusion that all you need to do is take some stool, to put into a rapid sequencer, an hour later come up with the microbial content. I'd like to note that these curves here are all spline, best guess, highly competent averages. If you look very closely at the central tendencies here, there's not too many dots on those central tendencies, and the population, as I showed you, is highly, highly unstable. It's kind of like the United States Census. The geographic center of the United States is in a small town called Hartville, Missouri. All the people on the West Coast, all the people on the East Coast, the geographic center where everybody lives is Hartville, Missouri. Nobody lives in Hartville, Missouri. So we may not be able to take the stool and say, you are at high risk of getting neck the way you've grown up, considering your blood culture is positive. We get that. And in the end, we now have an opportunity for the first time to do microbiologically informed prevention of this bad coming in, or promotion of the good microbes or their products to prevent this horrible, horrible disorder. Again, thank you for listening, and I'd like to thank my team.
グラスワイン、はい、赤で。
赤で。はい、かしこまりました。
So we're going to move on and talk about a virus that most of you have heard about in the news recently. It's the Zika virus. This is a really interesting area because the virus has been around that we have known about for at least 70 years, and yet we don't really know much about what it does and how it does it. But we have most recently heard from the Centers for Disease Control that it has been implicated through epidemiologic correlates as a definitive cause of microcephaly in infants, of pregnant women who have been infected. And so we are very excited to have Dr. Desiree LeBeau, who's an associate professor here in my division. I was very fortunate to recruit her to Stanford about a year and a half ago. It hasn't been long, but she's already making a major mark in her area. She's a pediatric arbovirologist, so works in areas around flaviviruses, which are related to the Zika, and other viruses as well that are transmitted by mosquitoes. So welcome to Desiree.
Hi. So good morning, everybody. It's my pleasure to be here to talk to you about Zika virus. I really believe that we're living in interesting times right now. This is the first time in my life that I've been able to witness the discovery of a novel teratogen, a new congenital infection. Some of you in the audience may remember when rubella was discovered, sort of mirrored what we're seeing now with Zika. And as a mother of three, I can say that baseline, I think pregnancy is a time of a lot of anxiety because there's no control there. There's so many unknowns. We've been talking about this over the last couple of days. There's so many things that can go wrong. Most of the time, things turn out right. It's a miracle, the miracle of life. But now we're sort of witnessing when things go wrong. And there are a lot of pregnant women right now in the Americas that their pregnancies have become a terrifying state for them. And so we're going to learn a little bit about Zika today and just keep them in their mind as we talk about this today. So I'm going to start just with a little bit of arbovirus background for those of you who are not familiar with arboviruses in general, and then we'll move on to talk a little bit about arboviral disease emergence, and we've seen a lot of these viruses over the last couple of decades, so I'll talk about that. And then the meat of the talk will really be focused on Zika virus infection. I'll bring up background, we'll talk about the current outbreak, and then we'll discuss transmission, risk factors, and then some more clinical data. How do we diagnose it, what can we do treatment-wise, and then I'll finish up talking about really the future of Zika research. First, what are arboviruses? Arbovirus stands for arthropod-borne virus, and these are viruses that require a blood-sucking arthropod to complete their life cycle. Many of these infections are zoonotic, which means that they can attack humans, but also a lot of animal species, and it can have harmful effects in those animal species. We know of about 500 viruses to date, and they come from 8 very diverse viral families, but 3 viral families in particular, the Flaviviridae, the Togaviridae, and the Bunyaviridae, are what are responsible for most of the human disease when it comes to arboviruses. I put up some life cycles here. I'm not going to go through these in detail, but just to demonstrate to you how different life cycles can be. All of these viruses are spread by mosquitoes, but in fact they have very different life cycles, and this becomes very important when you think about controlling these infections, because the vectors themselves, the mosquitoes, can have very different behaviors, which is important for vector control. If you look in the far right, the bottom right corner, that's the West Nile cycle, and you can see there's this cycle between birds and Culex mosquitoes that we sometimes get infected as accidental hosts. Compare that with Rift Valley fever on the left side, you can just see that these life cycles can be quite complicated. Now, the dengue life cycle, which is a flavivirus that's closely related to Zika, is in the upper right. You can see that there was this lymphatic cycle that then led to an epidemic cycle, and that's pretty much what we're seeing with Zika. It's just this epidemic cycle. So it's the mosquito, Aedes aegypti, and humans then get infected from the vector and then are able to infect uninfected mosquitoes that then go on to become infected and then spread the disease to new humans. And so we don't need this lymphatic cycle to really see this. This epidemic cycle can just cycle on its own, and that's what we're seeing. So let's just talk a minute about the vector, Aedes aegypti. This is what it looks like. It's actually a quite beautiful mosquito. It has these spots on its legs and limbs. And this mosquito has really emerged over the last several decades. You can see in the 1930s it was widely distributed throughout Central and South America, and then by the 70s it has really contracted, and that was really because of the use of DDT. And then by 2000, again, it has emerged all over Central and South America, and you can see in the bottom panel there, we do have this vector in the United States. We think that the reason why this mosquito is spreading so rapidly might have something to do with insecticide or drug resistance. It could be that the planet's warming, maybe there's more habitats. And then finally, I think a lot of it has to do with the shift from prevention to emergency response. So instead of sort of surveying for these mosquitoes, trying to keep their populations as low as we can, we sort of only really put a lot of effort toward it once there's been an outbreak discovered, and that's often too late. There are some very specific vector behaviors about this mosquito that make it a very efficient transmitter of disease to humans. So I just want to bring those up first. The life cycle of the mosquito is quite rapid, so it goes from egg to adult in 13 days. Sometimes in warm climates, that can happen in about 7 days. So you can see all of a sudden you can have thousands and millions of mosquitoes quite quickly. The eggs are very, very hardy. They can remain dry. They're very desiccation resistant, and they can remain that way for years and still be infectious. The mosquito is a bit of a homebody. It only flies about 100 meters from where it's born, and so that's important for control, but also it's just important to know that that very local environment, even in your backyard, is actually important to transmission risk for humans. Another thing about this mosquito is it's very anthropophilic, and what that means is it just prefers to feed on us. It loves human blood, unlike other mosquitoes, which sometimes feed on other species, of course. And finally, it prefers to breed in man-made containers. So if you have a flower pot in the backyard or a dog dish, it only takes about a tablespoon of water for this mosquito to lay her eggs and for them to develop. And so they're homebodies, and they love to live in and around human habitation. Finally, this mosquito is sort of a nervous Nellie, so when she bites you, if you happen to move your arm, she'll fly away, and then she'll go bite another person and another person. And it turns out, on average, it takes her about 4 to 5 bites for her to get enough blood and enough protein to have a successful oviposition. So that means she could have transmitted Zika, dengue, chikungunya, yellow fever, whatever she might be carrying, to 4 or 5 people to just have one blood meal. And these mosquitoes bite during the daytime. So many people say, oh, mosquito nets. Well, mosquito nets work for the malaria vector, which is the Anopheles mosquito. But these mosquitoes, Aedes species, bite during the daytime, dawn, dusk, and during the day. And so a net is not going to be the cure-all. We unfortunately have these vectors here in California. Just bringing a little home to you. So we have them in Menlo Park and Atherton. And then also Aedes albopictus, which I'll talk about in a minute, which can also transmit many of the infections we're talking about, is also been found in Southern California. So this is Aedes albopictus, a close relative to Aedes aegypti. And this is the Asian tiger mosquito. It has a temperate distribution all throughout North America. And in the U.S., it's really expanded, again, very rapidly over the last years. It was initially introduced into Texas in the 80s, and then over about 20 years, it established itself in 26 states and 866 counties. And so this is just a map. The top is just showing the Aedes aegypti distribution throughout the world, and the bottom is showing Aedes albopictus. You can see in the United States, Aedes albopictus is more of a problem for us. Are these infections important? Well, I'm here today talking at this very nice conference, so it must be important to someone, but actually these infections affect a lot of people. So over 1 million people die from mosquito-borne diseases every year, and that a lot of them are children. Children are at very high risk for these infections because they're outside and they're getting bitten by mosquitoes. We've seen what West Nile can do when it came here in '99 and how it spread across the U.S., causing a lot of impact in health costs. And so now there's more deadly arboviruses that are coming our way. Important to know, though, although these viruses are globally distributed, if you don't have the vector, you're not going to have the infection. Unfortunately, here in the U.S., we do have some of the vectors, so we need to pay attention. Over the last 20 years, we've really seen a dramatic resurgence of these infections, both in humans and in animal populations. And these are epidemics thought to be caused by arboviruses that we thought were under control, like Aedes aegypti. So Aedes aegypti spreading dengue, yellow fever, and now Zika. Or other arboviruses that have expanded their geographic distribution, like West Nile when it came here in the 90s, or Rift Valley fever is emerging in the Middle East, or chikungunya through the Americas, and so forth. And there are also new viruses that are being discovered all the time. Why is this happening? I think a lot of it has to do with the influences of modern life. So we live in a much more urban than rural world now, and that has its implications. We change our planet all the time: deforestation, reforestation, land reclamation, irrigation projects, and so that, of course, can change vector habitats. Unfortunately, there's a lot of military activity and war in our world, and so that, of course, disrupts any sort of surveillance and control that might have been going on beforehand. Climate, extreme weather events, natural disasters, again, can alter habitats and make it possible for vectors to breed. And then finally, we have a very limited toolkit when it comes to vector control. And I'll bring this up at the very end of the talk. Not to mention, we live in a very small world, right? The world is small because everybody's moving all over the world all the time. And this is a picture of just 24 hours of air traffic in the world. And you can see 2 billion people travel on airplanes every year, and so can these infections. And this is exactly how viruses get around the world. Oftentimes, they come in a commercial jetliner in a person who's either having symptoms of their disease or not having symptoms. And they get back home with the person, or they go to a new place with that person, and if the vectors happen to be there to bite the person who has the virus in their blood, that's how outbreaks can begin. Now, West Nile, most of you remember West Nile, which predates this slide when it came in '99, but you can see this is just a slide showing major re-emerging outbreaks, disease outbreaks, and many of them are actually arboviruses. So there's West Nile, which isn't even pictured, and then there's chikungunya. I don't know how many of you have heard of chikungunya, but it's a very important tocovirus, which is emerging right now. Initial outbreaks were when it emerged in Europe, and then we're having outbreaks right now concurrent with Zika outbreaks, although you can't tell it from the news, but there are over 2 million cases right now of chikungunya virus in the Americas. This is the first time this virus has ever been outside of Africa and Southeast Asia, and it's emerging through the Americas and causing a lot of problems. This virus can cause very long-standing joint complications. And now we have Zika. So First, there were the outbreaks in Yap in 2007, which is when I first heard about Zika, and now we have outbreaks in French Polynesia and Brazil and Colombia. So what is Zika virus? Well, as Bonnie mentioned, Zika is a flavivirus. It's a single-stranded RNA virus, and it's very closely related to dengue, yellow fever, West Nile, these other flaviviruses that we know of that have important and toxins in them all. It was first isolated in 1947 when they were doing yellow fever research in the Zika virus of Uganda. So they had monkeys in cages, and they were looking at several monkeys, and they were actually trying to isolate yellow fever. And instead, they isolated and discovered a new virus, and they named it Zika because it was isolated in the Zika forest. Phylogenetic analysis really suggests that Zika is kind of a new virus, and originated as early as the 1920s. And there are two strains. There's the African strain and the Asian strain. And what's going through the Americas right now is closely related to the Asian strain. As I've mentioned, it's transmitted by Aedes mosquitoes, but of course there are other possible transmission methods, which is why I'm here talking to you today. So there are perinatal cases, which I'll be discussing. There's also transfusion-related risk, and then there's sexual transmission, which I won't spend a lot of time on, but others to say that there have been cases now confirmed of male to female sexually transmitted Zika. And this is because serum, urine, and semen can harbor the virus for undetermined lengths of time. And this it's definitely a possible way of spread, but probably is not an important cause of the spread that we're seeing right now in the Americas. These are just some maps sort of showing, I don't know, do we have a pointer? Probably not. Well, in this sector there, where it says 1947, that's Uganda, and again, that's where the virus was initially isolated from this monkey. And then for the next 20 years or so, there were sporadic cases through Africa, a few human cases here or there. And it wasn't really until 2007, when the virus hit Yap, that it really started to garner some attention, at least in my field, among arbovirologists. And that was because during the Yap outbreak, although Yap, maybe many of you have never heard of Yap, and I'll show you where it is, right here. It's at the top left there. It's a little Micronesian island. But what was interesting about that outbreak is that 75% of the island was infected. So just such a high attack rate. There's only 3,000 or 4,000 people on the island, but still 75% of them. And so it really garnered a lot of attention. And then what happened is you can see it sort of crossed the Pacific Ocean over time, ended up in Easter Island in 2014, and then in Brazil in May of 2015. And then since that time, it's spread like wildfire, just like chikungunya, up and down into Central and South America. And right now, there's about 2 million cases or so of Zika reported. So what does Zika look like normally? The reason why people weren't paying a lot of attention to this virus was because the clinical manifestations are usually quite mild. So just like dengue, about 3/4 of the infections are asymptomatic. So if 4 people have the virus in their blood, only one of them is going to have symptoms. And so the people who actually do have the symptoms, they sort of have what I call a dengue-light syndrome. So it's really not as severe as dengue. It's maybe a couple days of high fever, but then it's only a couple days long. You may have an itchy red rash, red eyes, some muscle pain, some arthralgias, but then you get better pretty quickly. Severe disease is quite uncommon, and there haven't been any reported deaths due to Zika in adult populations. This is just some pictures just showing you sort of the types of rashes and the conjunctivitis that you can see with this infection. Now, why I'm here talking today, of course, is the link between Zika and microcephaly. So first, what is microcephaly? So microcephaly just means that the occipitofrontal circumference, so the baby's head circumference, is less than 3rd percentile based on standard growth charts for sex age and gestational age. It's generally a pretty rare condition, and babies are born with small head, or the head can just not progress in growth as time goes on. And of course, this can result in severe developmental delays. This is data that a Brazilian colleague shared with me early on when they first started to note this association with microcephaly. And so what we're looking at here, at the beginning of the time, you see that there's just this outbreak of rash and fever. And so the Brazilian government has seen dengue and chikungunya in the past, and so they were checking for all those things, but things were dengue negative. So, well, what is this, And you can see it took several months, but then by the 21st week, Zika had been confirmed. And then they noticed several months later, of course, that there was this peak in microcephaly cases. And right now, there are supposedly more than 4,000 cases of microcephaly just in Brazil alone. And when you look here, you can go back and see that many of the women who delivered them with these microcephalic babies were probably infected in their first trimester. So there was this temporal association, nothing causal, but just a temporal epidemiologic association. And then studies began to come out showing Zika virus being isolated in the amniotic fluid of babies who had microcephaly. And this happened in Brazil, and then also looking back in French Polynesia. And the babies that were born the abnormalities in the brain included brain atrophy, calcifications, problems with the cerebellum, the deep brain, corpus callosal problems, and so forth. So just really dysgenesis of the entire brain. And here's just some pictures just showing some of those calcifications, the very thin cortical structures, and then the dysgenesis of the corpus callosum and the fauna.